We are finally ready to make a solution, and this is described in XAML in sections 6.1 and 6.2. So first of all, a little bit of administrative things. We have pure. How do we distinguish between whether a substance is pure or whether a substance is dissolved? And a pure solute may be either solid or liquid or gaseous. So a solid might be an example, sodium chloride in your salt shaker, right? A liquid might be ethanol. Ethanol is pure alcohol. That might be pure, that's a liquid. Or gaseous might be carbon dioxide, CO2. Now, after it's dissolved, it's a different situation, because the sodium chloride, the ethanol, or the CO2 are now in water, and we need to indicate that somehow, and that's done by writing AQ behind it. So if I write CO2 gaseous goes to CO2 aqueous, that's actually a process. It's sort of a thing between a chemical and a physical process, because this CO2, it's not really a phase change, right? Gaseous to liquid, that would be a phase change. That is a physical process. But gaseous to aqueous, so the CO2 is now making an interaction with all the waters that surround it. So that's a bit of a change, of a bonding in the surroundings of the CO2. So there's a bit of a chemical process in there. But this could be CO2 from the atmosphere dissolving in the ocean. And so water is implied here. The AQ always means two things. First of all, water is implied, and that's why many people like to put water on the arrow, especially for beginners. But the pros don't put the water on the arrow. The AQ is sufficient to say, hey, water is implied. And the second thing that means is that this compound is actually water soluble, which is information, right? Valuable information, because many things are not water soluble, they are water insoluble, and they can never become AQs. So there would be simply no reaction. If something is not water soluble, you would go, this thingy reacts. No, it doesn't react. No reaction. Okay. So let's start with something, an ionic compound that is soluble. Salt. Salt from your household. Table salt. And I start by adding a few grains of salt. Let's say a spoon of salt into a beaker. You can do that at home. You probably don't have a beaker, but you have a glass. You can put some salt here. And if you had a very good, there is no real microscope to do that. You can, no light microscope, but an electron microscope will resolve this. Then you could see this, that the chlorides will kind of make a tight packing, and the sodiums sit in the holes, the sodium plus ions. So this is exactly what I've been talking about. Chlorides, there are chloride units and sodium units, but there's no sodium chloride units kind of packing together. That doesn't exist. And then I add water. So this glass is dry. This beaker has now water in it, and the sodium chloride has dissolved, of course. Somebody stirred this glass or waited just long enough. And then the sodium goes swimming and the chloride goes swimming. And this breaks, of course, apart into the ions, right? Because it consists of ions and it breaks apart into ions. And this is written as sodium chloride solid. And then what goes into water? Well, sodium plus ends up in water and chloride minus ends up in water. And that's how I'm going to write it. And this is called an electrolytic dissociation. And I should have written this out here. Electrolytic dissociation. And highlighted that because that's really important. It's called a dissociation because I'm breaking the ionic bond. So the ionic bond is broken, and it dissociates. That's what this term implies. It breaks apart into its components, into the sodium plus, into the chloride minus. That's what the dissociation part means. The electrolytic has to do with it breaks apart into electrically charged particles, into something that is positively charged, a cation, and something that is negatively charged, an anion. So this is the important bit here: positive and negatively charged product in a process where a compound is broken apart. So it's not really broken apart, it's just sticking together here, but the bits were already there. The bits are just now freely floating. So this is called electrolytic dissociation, and that's a new term. A new term, new vocabulary. We will use it whenever we write such an equation. A solid salt goes into water, and that's called an electrolytic dissociation equation. So let's look into this electrolytic dissociation at a little bit more detail. Imagine I had a very good microscope. I don't. That's impossible. But imagine we can look at that. So then what's happening at this molecular level? I can see this little crystal here, and it's negatively charged ions and positively charged ions. And now the water comes, and each water molecule has a negatively charged side, the oxygen side, and a positively charged side, the hydrogen side. And the hydrogen side can attack or surround the negative ions, and the negative side can interact or attack the positive charged ions. And then the positive ions go swimming or go floating by being surrounded by oxygens, and the hydrogens are pointing away, and the negative ions go swimming by being surrounded by hydrogens, and the oxygens are pointing away. Now, this artist didn't quite know what he was drawing, because each water points just one hydrogen at a negative ion. But, well, this is good enough. So, but this is a very important graphics. If you understand the concept of this graphics, you understand electrolytic dissociation. Study this graphics, it's in your book. If you understand this graphics and really know what every aspect of this graphics means, then you understand electrolytic dissociation. And this is this kind of, oops, that's not what I wanted to do. I wanted to do this. And this equation here describes that graphics. If you understand this relation between this equation and this graphics, then you understand electrolytic dissociation. What does it mean for a covalent compound, right? What essentially the same happens, right? The components, the units of the sucrose crystal go into solution. I take sucrose because that's in your sugar bag. Your sugar bag, you can put sugar in a glass at home, you can stir the sugar, and the sugar will dissolve, right? Sugar is one of the water-soluble molecules. It's sufficiently polar because of all its OH groups to be water-soluble, and then the water will surround each sucrose unit and the molecules, but the molecules are neutral units. They're not positively charged, they're not negatively charged, and more importantly, the water doesn't break the molecules apart. The molecules stay whole. So we have sucrose molecules floating in water. And that's what it looks like. We have a sucrose molecule, a whole sucrose molecule. It's not broken apart. It's unchanged. It's the same as it used to be in the sugar crystal. And we have water. Those things are big and neutral. Water is small and neutral. There's only neutral things floating around. Nothing is charged here. So nothing is electrolytic and there's no dissociation going on. So that's the big difference here between ionic and covalent. So here's my summary. We have a soluble ionic compound. Let's consider soluble covalent compounds. Soluble is not something that you can kind of assume. There's different rules here. They're complicated. We will talk about them in the future. But for the time being, let's compare soluble ionic with soluble covalent. Then the units are ions. They float in water and I get charged units floating around in water. Here, my units are molecules. They float in water and I get only neutral molecules floating around, only neutral units. This is the product of my dissociation equation. I broke the ionic bond. Sodium plus, bromide minus. I made aqueous, right? This is very hard to do if you don't do it with water, right? If you just try to do this by heat, this is not happening. Forget it. It breaks apart into atoms. But if you do it with water, it breaks into ions. Sucrose just doesn't break apart. It stays whole. It just floats. And this process, because it breaks apart, is called dissociation. And because the dissociation products are ionic, is called electrolytic. All right.